Okay.
I just want to say welcome to everyone. Thanks for coming, and I won't hold you up. I'll hand over to Boat and Co to kick off with Scala.
No, not me. Next month. Okay, we will have the Scala workshop next month. I'm not sure the date. Pinin, which date? 19 next month, if anyone interested. But for this week, we will the functional programming principle by คุณรวิทัศน์ขอเชิญคุณรวิทัศน์ครับ
Hello everyone. Well, I didn't expect that I had to speak in English, so, well, sorry for my rusty English. I haven't been speaking for a while. Okay. Well, it's maybe better if I don't use it at all, maybe? Okay. Yeah. Brilliant. Because, I always dislike the microphone, because every time I pick up the microphone, but I start singing or everyone starts sleeping, because I have to speak too monotone for my low voice to speak loud, right? Okay. Sorry everyone that I didn't expect to speak English today, so sorry for my rusty English. And if I'm speaking too fast, well, you can tell me I'm speaking too slow, you can also tell me, but since we got a lot of things today. And also, sorry, excuse for my daughter, she's my, Okay, well first, let me start by saying this. Well, I guess most of you probably heard this phrase for uncountable time when you study in college or studying programming that, well, C is a high-level language. C is a high-level language, and I really mean it. And what is lower? Well, better question, what is higher than C? Any guess? Well, of course not scalar. Of course not scalar. Any guess? Any other guess? Well, someone would say C++. Because I++ return 1. Root always return the same value, right? So C++ is the same C. That makes sense to you. Anyway, what's even higher than C is, well, assembly. Assembly is even higher, and I really mean it. Because I know there will be real-time voice filtering when I say the word, right? So you have to be the myself. Okay? And people say, are you crazy? Are you crazy? Should the assembly be lower? And, well, if assembly is higher than C, then what is lower then? It's actually a node from a certain point of view. And which point of view is that? This thing. You have any idea what this thing is?
Turing machine.
Wow. Great job, sir. It is the Turing machine, and so that's the introduction to my talk today. The functions and the machine. But we're going to start from the machine's perspective first. Because that's where, from our perspective, it's the lowest from the other side, right? It's like, it's like I'm being a time when I first go to US, well, when I was like, when was it? Oh, ages, I feel old. When I went to US over 20 years ago, well, everything was shock, and I have to learn to speak in their way and think in their way to bring in their culture. When I went to Japan 15 years ago, maybe over 15, well, I feel old here. Well, I had to start thinking in their way, not just learning their language, understand their culture, how their people really think, to really work with them. So since we are all working in a machine, in, well, maybe 1980s, 1990s, and even before half of you in this room were born. So let's start from their perspective, right? And to start from there, I won't go into the first computer that was actually built, that developed, the ENIAC, whatever. I will go a little bit underground. That's the theory of computation. We'll talk about the models here. The first thing, like most of you should already know, the granddaddy of the finite state machine of them are this one. Any idea what it is? Well, probably the same answer you already answered, right? You've seen this before, right? Who haven't seen this one before? Okay, so I guess most of you should probably seen this already. Well, if you don't know what it is, I made it a little bit easier for you. Sorry for my bad handwriting. It's from my breadboard I showed yesterday. So, well, maybe it's still not too easy, right? It's mathematical models of the Turing machine. Well, let's explain it in a little bit layperson term. Okay, yes, right. First thing, we got the machine with the finite state. That's the cube. Okay, it starts in some certain state to 0. Well, and in order to know this, it really ends the process. It's working. It's got to be some final state, right? It's got to be some final state. It may be one cell, it may be several, but it has to end in one. Okay, it has to be the subset of this one. This guy. Okay, that's the state. Well, next we got another state. Next we got the all values that it knows. It doesn't know anything else other than what's specified in this. Okay? This is all values that it knows. If you put A, B, and C in here, that's all it's going to know. It won't know D, E, and F. Okay? It's like when you grab a student nowadays, you want to know A, B, and C. See? D and F is taken out of the transcript, right? So, well, being a college professor, have to make a joke. All the values knows, and where is it in the machine? It's on the tape. Tape is for input symbols and also memories. Okay, it's also memories. Well, it has to include the blank symbol. So blank symbol, the noun. Okay, the noun. It's when you program and do another L or NIL, whatever. Okay. And next thing, this one, well, probably should use it's too slow. Sorry. Oops. Okay. And if you use only this portion of the symbol it knows for the input, okay, and it can be blank. Then this is the value that it knows. The heart of this is this one, this guy. We call it the transition table, the transition function. What it does is that if the machine, okay, oh, candy. Well, this machine is in some stage, and it found some symbols. Then it transitions the machine into the next stage, and write some symbols, and also maybe move the head. Okay, maybe move the reading head right here. So, well, after that, it will be in new stage with new value written to memory or read from. That's it. That's this. So, well, the machine finite state, the tape with inputs, with the symbols for input the memories, and the transition tables. That is sounds something familiar. Well, I bet my 2 cents or maybe my account, I think most of you know the answer. Most of you have seen this before from somewhere, right? Is there anything so similar? Is there anything so similar that you're familiar with? I give you a big hint, okay? I give you a big hint. something like this, right? It's probably seen something like this when you decompile a program, when you check your the dump debug trace of some of your iOS application nowadays. Well, you've probably seen this the last time when you studied the MIT simulation in college, something like that, right? That's it. An assembly is an almost exact replica or abstraction of the Turing machine instruction, how it works, basically. So, well, that's the highest level, that's the highest level instruction from the Turing machine perspective, right? When we see the when we look at that instruction, we might not know exactly what it is trying to accomplish. We know how it works, but we don't know what it's doing. Okay? Obviously, it's moving here and there. It's moving to that memory, writing this down. It's moved to that, reading that, put into other stage. If in that stage, it goes to that way, right? So we don't know what it's doing. Well, the thing is, at the core, there's one Turing machine. There's at least one Turing machine for solving any uncomputable problems. Okay? One Turing machine computes one problem. And the one that takes other Turing machine as input and have can emulate it, it's called universal Turing machine, UTM. Well, I'm simplifying a lot of things here, okay? Well, it turns out if the problem is computable, there exists a Turing machine for solving it. Means if the problem is solvable, you can build a machine to solve it, right? It's possible to solve it, to build a machine. Well, it might be so hard to build a machine. We are not talking about easy or hard. We are talking about possible or not, okay? It's like, well, you want to get married to Amkasharapa or something, okay? It's possible, right? But it's probably so hard to most of you. Our equation is not possible for me already married, so. Check that out in the video. Thank you. Okay. So, put it simpler. If the problem is computable, then the machine exists. Okay. If the problem is computable, then the machine exists. Well, to build a really useful one, you know, the mathematical notation, the models on the blackboard, it's all that good, right? To really build a useful one, like this, it's a UNIVAC machine. To build a really useful one like this, well, we got to go to electrical, right? And doing some really nifty, sophisticated machine code instruction, electrical instruction for that to operate. So basically, it's all boiled down. I'm oversimplifying here, but the thing is, this is how it's boiled down to 0 and 1. Well, let's put this together a bit. Okay, let's put this together a bit. We build this, but is there any of you who want to program in something that really close to this forever? Yeah, I saw some grin. So it's probably me. I want that. I want challenge. Yep. There are so many programming languages I can't emulate that process. You know, like malware. I can't produce them correctly, but you can try something like white space programming language or brainfuck or whatever. Okay. So obviously, most of us, right? That's why we learn things like scalar and something like that. We learn how language from our perspective is that. We didn't want to program this kind of thing forever. So we abstract this, okay, into something that's easier for us to understand and to translate to their language. Okay. Well, remember this? Assembly is even higher. It's from their view, not from ours. From their view, not from ours. From our, because we are two different types, because we are in two different end of spectrum, right? Us and machine. So things that higher level for us will be lower level for them. Things that higher level for them will be lower level for us. Okay? So that's the machine. Well, from their point of view, the lowest level is If you're talking electrical engineering, it's talking about machine code, right? The signal. If you're talking about computation models, that comes the Turing machine instruction, and that's the lowest you can go. Okay. Then we start abstracting this into things we call assembly. Down the line, for years and generations, okay, for years and generations, we had to think the way they do. They being the machine. Well, I'm not trying to differentiate us and them right now because there's no Skynet yet. Okay, there's no Skynet yet. And obviously, I'm not John Connor, so I'm not trying to differentiate us and them. But you know, for years we have to think like them. Ironically, right now we are trying to teach them to think like us, right? In the AI and things. Okay. Well, we try our best to abstract it for the way communication to be closer and closer to our languages as possible, right? So there comes dot 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 dot. I don't know what it is. There comes dot 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 dot. Okay. Well, if I'm talking dot, most of you will say .net. No. Some of you, but I know that everyone is still using .net now, right? So anyway. Some of you will say .a, well, internationally we call it Doda, or well, challenge me in online prayers sometimes. Yeah. Well, then comes C, okay? C is the pivot from my perspective. C is one of the first time that it's right there between the border. It's crossing the border because we abstracted it to the point where it's almost still like our language, right? You create an integer instead of you going to that memories and saying, well, I'm going to put values here in certain whatever addresses, and instead of putting some symbol and move back to create a loop, you can, use the for loop, right? You can use the for loop and, well, why this is true, we're going to do this, so it's almost feel like our language, see? And, well, if you want to go, if you want to abstract it a little bit further, you can even define ever, semicolon, so you can say forever, see? Okay, so you can abstract a little bit further, but the thing is, the language, the wording, the vocabulary is close to ours, correct? But is it really the way we think? Well, what the hell is this? Well, you look at the member function and give you a big hint. Do we really think like this? Do we really think like this? You know, can you comprehend? At the first glance, don't try to do the low level of manipulation, okay? Don't try to think your head like, well, it's lower, it's less than high, and I do what, and I move the pointer to whatever, and I subscribe. Don't try to do that. At the first glance, I give you 5 seconds. Can you tell what it does without looking at the function? Well, so, is that really the way we think? You know, all this kind of thing does. Is that, well, I have this room full of people, right? And I just pick this guy and one guy, maybe you. Well, you stand up, and anyone taller go to this side, anyone shorter go to that side, okay? And repeat the same process on both sides. That's what I think. Is that the way I think? No way in hell. So, since election is coming in US, not ours yet, so I won't know. Don't put me in jail, please. Don't put me in jail, please. I don't want to hear. I just want to know what this. Okay. So, well, thing is, can we start to stop thinking like them? Can we start to stop thinking like them? Machine animals. Because even though, no matter how we abstract the language is, closer to the way we say things, it's still not coming close to how we think it, right? How we say things and how we think is completely different things. The way of thinking and the way of saying. Okay? The way of saying is the word, the vocabulary, the structure of the language. The way you think is how, well, you're reflecting even something deeper, the process of bringing something out of something you've given. So, can we start thinking like that? Is there any other way, like this? Well, in my second time in my life that I saw the love at first sight, it was Haskell. And call me geek enough because, most of us will fall in love at the first sight, mostly with the girls or guys or whatever, right? Maybe a toys, maybe a movie. The second time that I had that kind of love at first glance, love at first met, at first sight, was this source code. It's in Haskell. Well, it's more like it, right? It's more like the way I think. You see? Well, if you repeat the process, right? Well, you have a room for people, you pick one guy, put him in the middle. Well, anyone shorter go this side, anyone taller go that side, then repeat the same process and goes. Okay? It's closer to the way I said it, right? Way closer. So, but the thing is, can we really think that way? Is it really possible not to go into machine abstraction? Because we still have to work with computers, that's a fact. Okay? Unless we can program people directly, we still have to work with computers, right? So that's it. So to do that, we look at the different side of the world. Well, in the theory of computation, probably most of you have studied only one model of computation, that's true machine-based, finite state machine-based. But there are many others, okay? There are many others. I'm emphasizing the S right now. There are many others. One of them is lambda calculus, okay? One of them is lambda calculus. I won't go into the depth of lambda calculus right now, but I just give you a rough idea how it works, okay? First, let's get back to school. Okay, let's get back to school. Well, if you see this kind of thing, if x equals 3x plus 5, then if I say, let's y equal 5, let's y equal 5, find me fy, what will you do? First, well, you say fy, okay, no problem. You rewrite fy into something like this, right? F5. Then you see F5. F5, you say, oh, I see F something. Well, it's similar, right? It's so similar. I see this pattern. I write this way. So this guy become this, right? This is how you solve it. This is how you did it in high school or middle school. Well, maybe today children nowadays may be studying this in elementary school. I don't know, but it was high school for me. So, how do we define function? Just that thing that we just saw, how do we define it? Well, that is simple. Ironically, we are defining function using a function. This is a function that returns a new function. So, this is a function that returns a new function. Okay? And this is about variable, meaning things that will be rewrite, okay, into this, okay. So right now, what we are doing, we are defining the rewriting rules. X rewrite to X, okay. X will be rewrite to X. The example you just saw will be written in letter form like this, okay? This will, well, just ignore this for a moment. We will rewrite this in this, okay? So how we use it? It's like a function. If we aggregate this, if you put this into one block like this, and we put 5, it's binding x to 5. So we are defining, we are saying less x equal 5. So if we say f equal or this, if we say f equal or this, then we are defining this thing. Okay? We are defining this thing. So that was the basis of the lambda. Like I said, I won't go into level of the lambda calculus yet because there's a lot of other things, okay? But that's how lambda works. You're defining function. Well, so basically, it's a transformation by binding and substitution. The calculation based on that. So, what I really want to say is that it's just like how you learn in math in high school. See? That's why I said I take you back to school. So it's just like how you did in school, every little details. The thing is, it turns out, if the problem is computable, then the lambda expression, the compute exists. Well, again, simplifying a lot of things here because if I really go into theoretical things, it's going to be the better induction, whatever, okay? So it's going to be a lot. I'm simplifying. That means the function is computed exists. Wait a minute. Wait a minute. That is stuff. Well, you heard this kind of thing somewhere before. If the problem is computable, then something exists. You heard this before where? Right. You heard this before here. The thing is, it's two different sides of the same board. See? Actually, it turns out the function and machines are equivalent. Meaning, if one thing is computable by one, is computed, there exists something in another end that can compute it as well. And this is called universal computation. You can look it up. Okay? It is provable mathematically as well. So, there are the two sides of the same coin. Okay? There are two sides of the same coin. Basically, the two sides are completely different. When you look at one side, look at the other, but it's still the same coin nonetheless. And they mean the same thing. Okay? When you go to shopping, you say something like 10 baht or whatever, and you put this, and you give the seller this thing. From this side, it's be totally different, right? It's nothing like another side, but it means the same thing. It has the same value. So it's two sides, the same coins. Then, so it means, basically means, so you can rest assured that even in the deepest abyss of the theoretical background, we don't have to think like that. But we can still not think freely, we have to still think in functional form. Okay? We have to still think in functional form, not think in whatever form. Okay? Thing is, so all I want to tell you is this. It's making sense of computation by value and functional transformation, just like I did in math, and that means if there is one takeaway in this session, is this slide, okay? That means no storage. When you do math, did you ever think of storage? No. No storage. No addressing memory. And the variable, when you say let y equal 5, you don't think that y hold the 5 value. But you say, whenever I see y, I write the 5. Right? That's how you think in mathematics. Well, for storage, the tape, addressing memory, also the head of the tape, and the values and the variable holding values is the symbol written on the tape is for the machines. Okay. Well, how? Well, I want to give you some rough example. Today I go out my way and use C to teach functional programming basics. People are going to say, are you crazy again? Actually, I am. So let's go. Because C is, C is starting point. C is low enough. If we really want to think like machine, you don't have to abstract anything. You can just go low level pointer manipulation, right? And it's still high enough that if we want to create our own functions and call it and always return new value, we always can. Okay. So when you say x equals 10 in this statement, most of us were taught that there's a box named x, and you put 10 into that little box, right? This way it reflects the low-level machine kind of thinking. See, there's alias, x is actually an alias of addresses. Then you go to that address via the alias, where the alias x, and in that memory space, you put 10 in there. So this is how most of us were taught when we start programming. Okay, me too, I was taught that way. But when I teach my own students, I teach differently, and MIT is doing the same thing. So, well, and when we see y equals x, what happened in our visual perception? What happened in our concepts, in our conceptual level? Well, since x is a box, so we create another box, right? We create another box called y, and we're going to move the head to the x space and see what value is in it, right? Take that, move the x, y space, take that value here. Okay. So in the end, there are two boxes. X and y each hold the value 10. That's how we used to think about programming. Now, this needs to rethink a little bit into what? Remember this? Fx equal whatever, let y equal 5. You didn't think, well, that's 5 space, store 1, call it y, stores 5 here, right? You didn't think that. Don't keep yourself, you didn't. Okay. Any objection? But you really think along this line. If I see y, I just rewrite it into 5, right? So whenever you see y, you rewrite to 5. This is more or less along this line that is your thought. So this means I will say let x equal 10. Well, is this kind of thing familiar to you in some modern programming language, maybe Swift? Let x whatever, right? So right now we are not allocating memories. We are not working below. We define the value. We defining the x symbol to represent this thing. So we just rewrite x into 10 whenever we saw it. So it's this kind of thing. X rewrite it to 10. And when we see this thing, what happened? You see x, right? You see x, you rewrite it into 10. So this happened. So since x rewrite to 10 and y also rewrite to 10. Really? Do you see it this way in your mind? Do you? Well, when you see the two 10s, right? Let's say that I have 10 fingers, and I have 10 fingers, and maybe if I'm Tosakan, I have 10 faces. Okay. Well, do the number 10 the same thing in my perception? It's the same thing. So it's not two different 10 that we are referring to. It's the same 10. Well, it's the same 10 because we are not storing it. We're just referring it to 10. Okay. So if you look at this statement, if you look at this kind of expression, in imperative way, imperative means the way of manipulating value. We are accessing the value in memories. Okay. Okay. We can manipulate value in memory. We do a lot of things in memory, and finally we return some value in some certain portion of memory back to us. Okay. So that's imperative programming. In the old boxes way, this is how we think. Okay, this is how we think. We access the memory alias via x. Let's see what is stored. We say with y, then compare the stored value, right? Because we are not comparing value, this is comparing what's stored in memories, okay? But here, if we use rewriting, if we see it in rewriting way, well, this is how it happened. So we're comparing 10 equal 10 values. Same thing. Well, let's see some example right here. Okay, first, we define x is 10, then we see y, right here you see x, rewrite it, evaluate it. Then, the next, well, there's nothing more you can do here. So you're defining this rule. Y rewrite to 15. So what happened here? You see y rewrite to 15. You see x rewrite to 10. Evaluate it? 15. Wait a minute. So you don't have to remember something that we used to call. You call by value, pass by value. Because, see, it's all value that pass. Okay? X and y is gone. Okay? It's rewrote already, so it's gone. So, above there, we are defining this x and this y to the value. So we are making the rule right there. Okay? We are making the rule right there. So whenever you see x in this code, you rewrite it to 15. You see y in this code, you write to 12. Okay. So it's something like this, something like this, something like this. Okay. Well, it works the same with pointers. It works the same with pointers, conceptually. Well, pointer used to be a deal breaker for most people start to study C language. Okay. When I taught you in university until 3 years ago, I used to teach for 10 years. Okay. The pointer is a thing that when I draw a line to pass, if you understand pointer, you can be in grammar. If you don't, you don't. For my class. Okay. Well, in the conventional way of thinking about pointer, in the boxes way. This is the box, right? So in the box is whole value. And px needs to be a box. But what value does it hold? It turns out it's going to be the address of the x. Okay, this made a lot of sense for people coming from assembly. This made a lot of sense for people coming from assembly. But when you think about people starting programming nowadays, they are so abstractly far from assembly, but why do I need the memory of the x? Why do I need to store and know the address in memory of the x? Why? Well, it's not pretty. So this way, you just have this. X is right to 10 and PS is right to x. That's it. So when you use something like pass by reference into say the swap function or even scanf, you are passing, well, oops, sorry. Well, you are passing this thing, and you will write into it itself. That's it. It's just one conceptual framework. Okay. The thing is, to recap what I just said, this thing like you did in mathematics, that's the basic functional programming. This thing like you did in math, there's no storage, there's no address memory, there's no memory holding anything. Therefore, no mutuality is given. No mutuality is given. Just rewrite to a new thing. Okay? It doesn't make any sense to begin with. Let's look at some Haskell. Okay, let's look at some Haskell. I don't know what use Haskell here, anyone? Okay. Let's have a beer. Okay. Let's look at some Haskell. Well, these are the toy example. You see that I'm a fan of the rich, some kind of richer thing. Yeah. What are we doing here? What are we doing here? Some say, well, we are defining the function lucky. But actually, we are not. We are defining the whole pattern. We are defining the whole pattern. Lucky 10, rewrite to Wayne Rooney. Well, you play FIFA, soccer, 16 or something, when Rooney scoring, going to be some, So we are defining this thing. Okay, we are not defining this function, we are defining this whole pattern. Lucky 7, rewrite into this whole string. Lucky 10, rewrite to this, lucky 7, and lucky whatever else. Rewrite into, sorry man, you're all that. The same thing with the same and the same thing with that factorial, okay? You are not defining the function, you are defining the whole pattern. Whenever you see factorial 0, you rewrite the whole thing into 1. When you see factorial n, you rewrite this pattern into this, okay? So when you see factorial 3, it's going to be 3 times factorial 3 minus 1, so factorial 2. The same pattern, you see the same pattern, right? You see this pattern, it keeps using this rule to rewrite itself. So in the end, it's going to be 3 times 2 times 1 and times 1, because it's factorial 0, right? Okay, let's look at a little bit more usual suspect in functional programming. Well, this kind of function exercises for those studying functional programming, right? You have to write this kind of thing in some certain point in your time. So let's look at one. Well, since usually I will put it to breadboard and write the evaluation live, but so you can pick which one you want. But right now, sorry, because it has to be in slides, so I can't let you have that. Okay. So let's pick one, the length. The length. We are not defining the function length. Rather, we are defining the whole pattern and enmesh the whole pattern. Okay. So we have the pattern right here. Okay. The pattern, the length of the empty list is 0. Rewrite into 0, and the length of whatever value begins, I don't care, and a lot of x. Oh, in Haskell, that's one convention. There's x concatenated to x. Well, people it's head and tail actually, but it's x and a lot of x. Okay, x plural. Okay. Well, what's happening is that we are defining this pattern x starting with whatever, I don't care, because we are not binding it into rewriting expression, right? We are not binding this thing into an expression we are rewriting. Okay? Unlike the previous slide where we had this. Okay. You can just say factorial whatever because you are rewriting it into this. It has to be bound variable. So anything, I don't care, but it is a lot of s come later. We are rewriting this whole thing into this. So whenever you have this list 1, 2, and 3, which pattern match this one? Rewrite to this because of this rule. So you keep rewriting until you get this, right? That's how it works. Same thing as this. This basic data structure is 3 and 3 traversal. See? Well, so you can define something like this. And if you have this 3 with the node 3 and 2 on the right, and 5 and 4, 6, right, by the 3. Well, if you do pre-order traversal, okay, of the now 3, it can be now y because you can define 3 either now or this structure. The 3 something will be rewriting into either this or this. Okay. If it comes with other pattern, then no. It's resulting in pattern matching errors or compile time errors, runtime error, depends on language. Okay. So we are rewriting this into this, and well, so you see how it works anyway. What about some Scala? I know people get crazy about Scala around here. Well, you got the stack, the basic data structure. When you're starting a new language, I really recommend starting from data structure. Well, once you got your basic language, syntax and basic expression covered, I really recommend starting from data structure because you already know how it works. Okay, you have to rethink it into another way of thinking. Well, we got the stack, and we got a lot of pattern. See, we got a lot of pattern, rewrite rules. When you push something onto the stack, basically, you return the new stack. With that on the top, right? If you pop the stack, see, if you pop the stack, not empty stack, that on the top, you see the pattern mesh? You see the pattern mesh? Okay? That the top is this, and the rest is also a stack. You got the rest, right? It rewrite into this, okay? Well, if you pop an empty stack, you said no, something like that. Okay, it rewrite into this, and when it rewrite, there's some evaluator. You take this and evaluate it later, okay? Well, now I got an S1 is equal to empty stack push 10. Push 1, push 7. So now I've got a stack of 10, 1, and 7, right? So S2 equal 1 the top, okay? So it's going to be equal to 10 and 1. Because this is top, this is rest, right? Well, right now, what the value of S1 and S2 after this, basically. What does the output say? What the value of S1 and S2 after this? S2 obviously will be 10 and 1. S1, some of you think it's the same. That's where you have to be cautious with functional programming. Because this is the real output. Well, S1, okay, S1, I call print at the 23rd line, right after I pop it. It still say 7, 1, and 10. Why the hell 7 is still here? You pop it already, why? But if we continue popping it, keep popping it until it's up to empty stack, okay? We look at it again, what the hell? And what about S2? It's 1 and 10. What's happening? Well, the thing is, we are defining the pattern. You don't have to think lower into the lower level, okay? There's nothing stored. This is the pattern we are defining. S1, rewrite yourself into this. Okay? So S1 basically got rewritten into this whenever you call it S1, right? This is S1. The real value S1 is this. So whenever you see S1, it's not S1 itself. It's this value. It's this value. The whole thing is one value. Okay? So when we see S2 equal S1 at top, it's not S1 right here. It's got rewritten into this dot pop, so it's become what? 1 and 10. Right? And we are defining S2 to this pattern. Okay? So right now, we think we are copying S1. No, you will write you're using pattern X1. Pop, so you got this. But it's not the value, it's not the same box. You are not copying from the box. Okay? You are not copying from that box. So if you think that right here, S1 has to be empty, and if you think right here, S1 has to be 1 and 10, you are still thinking in the box. It's the same X1, the same box, okay? Think of it another way. Remember. Well, something I got you. Impressive programmer will feel a little bit stressed right here. Because you're so used to accessing its areas of the same memory, right? So, well, the thing is, the pop just rewrite Alan rest to rest. Okay? Alan rest. See? Alan rest to rest. Right? The pop just rewrite the whole thing. Rewrite this pattern to this. It has nothing to do with the current stack. Just like that. You rewrite x to 5. It has nothing to do with x. Mathematics. To recap, this is it. Okay. To recap, things like you did in high school, in mathematics. To start functional programming, go back to mathematical basics because it's completely another end of spectrum. Don't kid yourself with the Turing machine base. Okay? No storage, no aggressive memory, no memory. I know everything we hybrid and mix up nowadays, but we are talking the paradigm of thinking, not some certain specific programming language that allows you to use imperative style in functional language. Okay? So, the lambda calculus is, well, basically the transformation by binding and substitution. Functional programming is the same thing. It's based on lambda calculus. Okay, it's based on lambda calculus. What I told you today is the basic functional thinking, not actual lambda, not the actual theory of lambda calculus. Okay, it's the basic functional thinking, the value and transformation and rewriting. One more thing. We're really missing from Apple's presentation. One more thing. I really hope you're going to say, one more thing, we start at the same price. Fuck you. Oh, sorry, I forgot to censor myself. That's rewriting fail, okay. Well, I actually believe we are thinking in a functional way. Okay, I'm sorry, the foreign is right here, a little bit tight. So, เอากระดาษแผ่นนี้ไปถ่ายเอกสารแจกทุกคนในห้องนี้ so basically you're taking this piece of paper and make a photocopy of for everyone in the room. You are not thinking of an imperative way in the way you're thinking. You are not thinking that I'm going to go to the operating machine, test it, blah 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 blah, right? More likely, it's going to be something else. Well, first you got a paper. How many copies you need? You count the people in the room, so you get a number right here. You pass it to the function, make a photocopy. Well, this piece of paper and number. So you get a bunch of paper and you pass it into this function, distribute it everywhere in the room. See? I actually believe that we care mostly about defining and transforming this value. So, this is the high-level language. In their world, for us, this is a low-level language. So, we have, I really think, to start functional programming, you have to start functional thinking, and that's basic mathematics. Okay, and that's concluded my presentation, and because it's the end, see I have to put the notes right here myself. If you see this termination, don't rewrite it further. Thank you. Vậy thìกลุ่มคนไหนงานจะได้มีใครจะได้ไหมครับแต่คิดว่าน่าจะได้ทุกคนเนาะผมคิดว่าไปช้าพอสมควรนะครับก็คือเรื่องของเรื่องคือ functional programming จริงๆแล้วเนี่ยถ้าเกิดว่าเราจะไปคิดว่าคือผมเท่าที่อ่านจาก tutorials จากหลายที่เนี่ยจาก documentation หลายที่เขาจะพยายาม base การสอนมันเนี่ยแบบว่าเฮ้ยมันไม่มี side effect นะไม่มีอะไรแบบนั้นเฮ้ยเราอ่านแล้วงงว่ะจริงป่ะหลายคนเริ่มอ่านสเตทเมนต์พันแล้วงงนะครับเพราะว่าเรากำลังแล้วมันมาแยก side effect คืออะไรมันใช่หรือไม่ใช่งั้นง่ายสุดเลยในการเริ่ม functional programming เนี่ยโยนอะไรก็ได้ที่เป็น programming ที่คุณรู้จัก based on ไอ้ model computation ที่มันเป็น address assessing อะไรนะ memory assessing เนี่ยนะครับทิ้งไม่หมด ไอมันไม่ใช่อะไรไปหาตำแหน่ง memory แล้วไม่ไอ doesn't make any sense นึกออกใช่ไหมอะไรแบบนี้คิดเป็น mathematics แบบ back to school ไม่ต้องการมากกว่านั้นถ้าเกิดอะไรก็ตามที่มันไม่ make sense ใน mathematics ระดับมัธยมนะครับมันไม่ make sense ใน programming ครับง่ายๆนะง่ายๆทีนี้ถ้าเกิดว่ามันมีเรื่อง high order function เรื่องอะไรแบบนั้นแบบนี้เดี๋ยวเจอกันที่โรงเรียนพ่อมด business school ได้นะครับขายของเล็กน้อย โอเคขอบคุณครับ
มีคำถามไหมครับก่อนเบรก Anyone have a question? Nothing question.
มีแต่เอาเขาไม่มาหรือไง
Everyone should have a question.
I have a question.
Yeah.
Do you think we should start to teach like functional language as the first programming language instead of?
Well, actually I do,
Okay.
and I did. Actually, the slide just saw. Well, because in the curriculum that I was given a curriculum, like our college professor need to teach according to the instruction in the curriculum. Even if I prefer Pascal or Scala, I cannot if the curriculum said C, and that's called MOCOR in right now. That's or MOCOR. This means มันคือเอกสาร rewriting to, okay? มันคือเอกสารที่ไม่มีใครอ่านไม่มีใครเอามาคอจาน okay? Thing is, that's the way of thinking that I've been using to teach C. Well, even though it's purely imperative language, you can still visualize it, understand it in the functional way. And so, when you're writing a function in C, you will accustomed to returning the new value. And not defining the same pool of memory and accessing the same pool from every function possible. It's called the global variable, right? See? So you accustom to that, and when you make a migration to the pure functional language, or more likely the hybrid language, like a lot of us have today, Swift, Scalar, and a lot of other things, it's becoming easier and safer as well. Okay? Did I answer your question?
Yeah.
Yes.
Earlier in your example, in Haskell,
Right.
I was thinking about, like, for example, if you were to do a Fibonacci function in Haskell,
Right.
That since it's just purely functional,
Right.
we're looking at big O n factorial operations
Right.
actually computed at the end,
Right.
versus if you used more imperative dynamic programming approaches, it would
Right.
be like way better, right? So how does functional programming kind of consolidate the
Well,
difference in performance?
the thing is, different in the spectrum needs different kind of optimization. Okay, need different kind of optimization. In functional programming, let's say performance and memory usage are one concern of many imperative programmers coming to functional world, right? As you say, the computation complexity is big O is one thing. The memory consumption is another thing because, well, people say, you keep spouting new values and you are not sharing anything. Wouldn't it be memory hog? Okay, that's two things that I heard the most. Let me raise the first thing first. Let's say, basically, well, for factorials and things, well, I was elaborate when I evaluated that thing, okay? What I'm going to tell you is that compiler knows better, because compiler knows better, because most of the time, since those two things are equivalent, and we have to translate one to another anyway, so you can almost guarantee the compiler optimization occurs at some level, because it has to translate into machine code. And also in functional code, that's functional algorithm. So if you write functional, the way you write imperative is going to be the best part, of course, because you are putting effort to already scrapping ground or something like that. Okay, I might have answered the exact question. Okay, but you can do something like tail recursion and things, and also many other things. Okay, and you can keep defining the value, so it won't compute again. Okay, it's like metaprogramming. When you define a function, let's found another definition. So that's dynamic programming. Okay, that's dynamic programming, so it's possible. Another thing, memory consumption. Memory consumption is concerned with most people. The thing is, well, the memory problem is real. But, the big but, it's not just in the functional world, it's paradigm world, memory is real. You know, the most problem with memory management is when can you erase one thing? Okay, when can you erase, delete object from the memory? When can you delete a certain object? It's a real problem, right? Because you cannot know, basically, you cannot know that this address of memory is still in use by whatever or not. And the real performance part is that if one process needs that value right there the way it is when it was called, you got to make the transaction log, right? So you have to log the access from everything else. Okay? So you got to log the access from everything else has to wait. Otherwise, this value might be mutated, it's volatile. See? Another thing is that, so when you got this value right here, and everyone access to it, so if one process doesn't need it anymore, can this go? No. Why? Because there's possibility that another process is using it. So, in order to counter that, we really need to put a lot of intelligence into the runtime and editing maybe in the language, and like in Objective-C we have reference counting and have automatic reference counting that migrate to Swift, and many languages use garbage collector, which is going to be basically if it never has to work at all. So you're putting more memory, so the GC doesn't have to work, right? So the thing is, the memory for imperative program, most big imperative programming project goes up like this. It starts right here, and go like this because pathing, you cannot delete the object easily. So it path, add more RAMs. The thing is functional. The thing is, that way of thinking is really the opposite of the spectrum. Okay, it goes up, but it spikes higher because it spikes higher. Instead of doing like this, it's called like this. Why? Because everything spawns a new thing, right? So it's going like this, but you can assure that it won't be needed afterward. So it's going to be like this. Memory footprint most of the time is going to be like this. Okay? Yes?
I think it's probably worth mentioning that the data structures in functional languages are usually implemented in a way so that they're sharing, like, if you want to append an item to a list by returning an entirely new list, the data structures are actually implemented in a way so that the entire old list is shared.
Right.
You're just basically only adding the memory for that one new element.
Right.
And then the garbage collector is keeping
track. Right. So that's true.